So I suppose I should introduce you. So I've known Mark for quite a lot of years, and I'm very pleased to have him presenting on our stream DB2 for ZOS data sharing performance considerations, it says here. Not the bit about having known you for a long time. Anyway, take it
Right.
away, Mark.
Can you see my screen now?
Yes, I can. You're not in screen show, but we can see your screen. That's
And now is it in
I think so.
screen mode?
Yes. Yes, it is.
Okay, excellent. And of course, I forgot to turn my video off ahead of time. So, oh well, you'll just have to see me throughout. So, welcome everyone. I hope you enjoyed lunch because I think that's what happened just before this. I'm going to talk today about some performance considerations for DB2 for ZOS data sharing. I'm with the Washington Systems Center, and I've been working with the DB2 data sharing for quite a long time now. The agenda I'm going to follow is a quick review of the parallel sysplex data sharing components and processes. This for anyone who isn't familiar with them, so they at least have some idea what I'm talking about. I'm guessing most folks will already have a good understanding of this. Then I'll talk about performance considerations, which is actually a relatively short section, because I'm going to spend more time on where you find the indicators. And I'm mostly using reports. I know when Martin did his session earlier today, he had lots of SMF fields and RMF fields that you would use in your instrumentation. But I'm assuming that most people are using monitors or other tools reporting. So I'm going to use that view. And I've got a few suggestions at the end. And while I do have time at the end for questions, Martin has agreed to watch the chat. And if you have a question, please put it into the chat. Because if there's something that you have a question about as we get started, it may be important to address it then rather than at the end. So quickly, what are the components of parallel sysplex and the ones that DB2 for ZOS uses? So first of all, we have coupling facility LPARs. These work as high-speed shared memory so that the information in the virtual storage of the two DB2s can be shared quickly. The CFs can be external, or they can be integrated, that is on the same system or KEK or footprint with other LPARs. They run coupling facility control code, which you can think of as a skinny operating system. They provide three different structure types: block structures, list structures, and cache structures, and DB2 takes advantage of all three. There are links between the CFs and the LPARs that are using the CFs. They can be external links, fiber, so those would be short or long. They can be quite long, or they could be internal. So if the CF LPAR is on the same machine as the systems it's talking to, then it just uses microcode, and those IC links are very fast. Everything about the CFs and the structures in them are defined in the Coupling Facility Resource Management Policy, or CFRM policy. We'll have some examples for some DB2 structures later on. Key ZOS components are Cross-System Extended Services, or XCS. Some people pronounce that SES. In South America, they pronounce it SHES. I don't pronounce it as an acronym. I say XCS because I occasionally go dyslexic, and I would hate to do that. A cross-system coupling facility is another important component of ZOS because that is how you interact with the CFs. That's how you do displays. That's how you make changes while it's in operation. The DB2 components within coupling facilities are the various structures, right? There's a lock structure, there's an SCA, and there are numerous cache structures. All of the DB2 data is shared. So there's one catalog and directory for the data sharing group. And of course, the user data would be shared. And then each DB2 member has read access to all of the logs, write access to its own logs, and read access to all the other members' logs. I've got a simple configuration here on the right with 2 members. This can theoretically go up to 32 members. I've seen up into the low 20s in my wanderings. So let's talk briefly about some of the processes that go on in DB2 data sharing. So the first one I want to talk about is global locking. And so this involves the IRLM address space of DB2 and the lock1 structure. There are 2 kinds of locks that we care about here. P locks are new with data sharing, and that determines whether there is interest in more than one DB2 in a particular resource. We call this managing coherency. So if two members have a particular resource and one member wants to change that resource, we're going to use plocks to track that. The interesting thing about plocks is that they're negotiable. If one DB2 has a plock in exclusive mode and the other DB2 wants to share it, they can negotiate and get to a situation where they can both participate with that lock. L-locks are old-fashioned DB2 locks that have been around since version 1, release 1. They're about managing concurrency. That is, no one's allowed to step on one page at the same time that someone else is stepping on that page. So we're going to have many readers or one writer. And in most cases, that's exclusive. Group-wide status is tracked in the shared communication area. The master address space is what pays attention to that. I'm not going to spend much time talking about that at all, because as long as you get even the basic definition correct, it's not going to be a performance problem. Too few messages to really make a difference. Buffer coherency is important, and that's where DBM1 and the local buffer pools and the group buffer pool structures interact. And again, the idea here is to make sure that the copy of the page that I have in my local pool and the copy of the same page that Martin has in his pool get updated appropriately, so that if I make a change, Martin is identified that his is out of date and he can get the new copy. So we have directory entries to track interest, and we have data elements to actually cache the changed pages. So when I change my page, I put it in the group buffer pool, it stays there, hopefully long enough for Martin to get it if he needs it. There are several options for defining these structures. Almost always customers will use GBP cache yes, and on the page set definition, it'll be GBP cache change. So we'll cache the change pages, but the other options are available, and in some other presentation, we could talk about them. So how does this work? I'm going to start with two locking examples. This is the no contention locking example. DB2A wants to lock a resource in exclusive mode. So XES sends a message to the lock structure and responds back to the IRLM, says you can have the lock. And the entry in the lock table says that DB2A or IRLM-A is now the owner of that entry. And DB2B wants a different resource, and now DB2B is the owner of that resource. And these messages, these little arrows, happen in microseconds. In a contention situation, right, I've locked a resource now in X mode for DB2A, and it carries on, and DB2B wants the same resource. And even if it's a shared resource, it'll be suspended, and that transaction will not proceed until the transaction on A completes. And when it completes, part of commit, it'll force the log records, and it'll unlock the resource, and it'll send a message over to B saying, hey, I'm done. And then B will go and register the lock, and now B is the owner of the lock, or at least has registered interest in the lock. And then finally, for our group buffer pools, it gets a little more complicated. I have a transaction that reads in a page from disk. DB2B can read in the same page. DB2A will, of course, lock the page before making changes. It'll make changes, and then DB2B has to wait because of the lock. And when DB2A completes the update, it'll write the new copy of the page out to the group buffer pool. You see the page has turned into page P prime, and it's in the group buffer pool. And as part of that commit, of course, it writes out the log records, releases the lock, but it also writes the page out to the group buffer pool. And XES will take a message from the group buffer pool and pass it to the hardware storage area in the LPAR where DB2B runs to say, hey, your page is marked invalid. So the next time DB2B tries to do a get page, it'll find out it's invalid, and it'll have to bring in the new copy, page P prime, from the group buffer pool. And then eventually, one of these DB2s is the cast out owner. So in step 8, DB2A will take that new copy of the page and write it out to disk for long-term storage. So to make data sharing work, there's some critical factors, right? The concurrency control, global locking, multiple readers or one writer. That's all about the lock structure. And coherency control, managing change data, that's a combination of the lock structure, making sure which resources are of interest in which DB2, plus in the case of the local buffer pools, the group buffer pools get involved. There are other coherency controls in DB2, like packages, for example. We do not have a global EDM pool. So those manifest differently, a lot more notify messages. Now, data sharing does incur overhead. That's because there are messages to deal with the concurrency and the coherency, lots of messages, thousands to tens of thousands of messages per second. So back in 2008, my personal record was looking at a customer port that had 166,000 synchronous lock requests per second. That was averaged over a 15-minute RMF interval. Since then, I've worked with a number of customers that have exceeded 200,000 or 300,000. And my personal record now is 411,000 sync requests per second over a 15-minute interval. So you know if it's averaging 411 over 15 minutes that it's spiking higher than that. I did see an email from someone where their system had over 643,000, but since I wasn't, personally involved in that activity, I can't claim it as my personal best. These messages, in the vast majority of cases, are synchronous. And by synchronous, I mean not only are they synchronous to the application, but they're synchronous to the processor that initiates the request. So the GCP or the ZIP that initiates the request of the coupling facility doesn't do anything else until the response comes back from the coupling facility. We used to call that dwell, now we call it spin, but it looks like CPU busy. And so the more of this you have and the longer it takes, the more time, the more CPU busy you incur for your workload. So that's why we care about all these things. So what are some of the considerations? Well, as I mentioned, synchronous requests to the CF are synchronous relative to the application. So of course the application is idle while this all occurs, but it's also synchronous to the processor that initiates the request. And the processor won't pick up any, keep running until the response comes back from the CF. So you want that back quickly. So I have a very simple graph here, right? And this shows as the number of members increase on the x-axis and the amount of throughput we're going to get, I'm calling it performance here, on the y-axis. You can see that this arrow is shifted off from the origin, and that's because there's a fairly large chunk of overhead, up to 10% generally, usually less, when you go from non-data sharing to two-way data sharing. Past that, when you add each member, it's pretty close to ideal, right? Ideal would be a 45-degree angle, and this isn't quite a 45-degree angle. And the question then is, where is your curve? When you're doing data sharing, how close to the ideal are you able to get? And that all depends on a number of variables. Things like your specific hardware configuration or contention rates, how much work is actually contending between the members of your group, how much locking and caching you're doing in general terms. And that breaks down to things like, well, how much time you're actually in DB2 versus the rest of the application, how much heavy duty sharing are you doing, how many locks does a particular piece of work need, how often are you actually sharing the data, are you doing lots of inserts and deletes? They tend to be more expensive and hold on to resources longer. And it also matters what release of DB2 you're on. And I imagine we could extend this and talk about things like coupling facility configurations and ZOS levels and so on. So those are all the things we care about in general. Now, if we look at our picture and the various resources here, there are other things that play into performance. The coupling facility link capacity. This was a very big deal in the mid-90s when data sharing first came out. And that's those lines between the coupling facilities and the LPARs. And you want to make sure that there's enough capacity for the message traffic not to be impeded. A coupling facility processor capacity can be an issue. I will point out a highlight there. And there are, if you're still running on a Z15, there's a reasonableness factor. You can't reasonably put more than 8 engines in a CF because the performance curve flattens out. If your CF processors are too busy, not only do the CF requests take longer to get serviced, but that means the host processors see longer service time and incur more overhead. Of course, we care about the DB2 structure allocation and definitions. There's the lock1 structure. We want to make sure that the table is large enough to minimize false contention because that drives overhead. And you want to have enough record list entries so you can track all the changes in the environment, so that so the locks will keep getting granted. For the group buffer pools, you need enough direct entries so you can track all the interest, right? In our two-way environment, if I have a bunch of pages and Martin has a bunch of pages, all of those pages need to be represented in a directory entry. One directory entry will track a single page anywhere in the data sharing group. And you need enough data elements to actually hold the pages that are being changed. So you can, if you get up to high write activity, you're not going to be impeded. And then there's another consideration, that is how far apart your systems are, right? Some shops, all of these are within visual distance in a room. Some of them are across the hall, some of them are across the street, some of them are across town, and some of them are farther away. And the farther away each system gets from its CF, the longer that response time is going to take. And as Martin went through earlier today, we're talking about 10 microseconds per kilometer round trip added to the service time. I'm going to focus on this set, right? The DB2 related considerations. That's because I'm a DB2 person. Now I know a little bit about link capacity. I'm going to show you a chart about processor capacity. But this is where I'm going to focus the rest of the session. So when you want to pay attention to your performance, where are the indicators? And again, I'm assuming that you're not a tool designer and that you're typically not writing things directly against the SMF or RMF data fields. Of course you can, but I just don't have them in this presentation. So the first thing I'm going to talk about is coupling facility displays and coupling facility reports. So the displays are typically an RMF monitor 3. There are other tools that will do this as well. Plus, there are the RMF CF activity reports. Now, what usually happens to me is that I end up looking at the data after the fact. So I use the coupling facility activity reports. I rarely get a call suggesting, well, we're having a performance problem next week. Will you come watch the monitors with us, right? Rather, it's the, hey, we had a performance problem last week. And so then I ask for the data and I look at the reports. Things that you can see in those displays reports include coupling facility request rates. That's interesting. CF processor busy. If the processor gets too busy, then all the performance is going to be bad. And the host processor cost and CPU cost that you pay for your software will go up. There's information on structured details. So you can understand if the block structure or the group buffer pools are behaving the way you intend. Of particular interest here is a synchronous service time, and this is laid out by LPAR, and the number of times you convert synchronous requests to asynchronous requests, right? XES will monitor your synchronous service time, and if it gets too high, it will start converting those to asynchronous requests. The good news about an asynchronous request is that the host CP, GCP or ZIP, is dispatched to do other work. The bad news is that particular request gets delayed, right? We still pay some cost to set up the async request, and it'll be longer before the request comes back, and therefore the application is waiting longer for the response. The structured detail explains about delayed requests, especially things for subchannel busy. And in the case of the lock structure, it will show contention and false contention. Now, contention is true contention means two different processes on two different members are going after the same resource, and there's not much you can do about that. False contention says that I'm going after a resource and Martin's going after a resource. They're different resources, but when you go through the hashing algorithm that Ireland uses to communicate with XES, they hashed the same value. Now, the good news here is XES can detect this and tells Ireland, hey, go figure this out. The bad news is that figuring this out is a bunch of messages and a bunch of overhead. And then finally, you can look at complex facility channel activity or link traffic, right? This is something that I glance at, but usually it's in someone else's responsibility to look at this. So let's take a look at some samples here. So at the beginning of a coupling facility activity report is the structure summary, where you get 2 lines for each structure. So I've got a couple examples with some DB2 structures here. Here is a shared communication area, or SCA. It's a list structure. And we've got some information here, like the number of requests over the interval. Here's a lock structure down here. So it's the same data sharing group, but the lock structure. And obviously you can see that the number of requests is much higher for the lock structure. Other information here includes lock entries, total and current. SCA doesn't have those. But with the IRLM, we can see that in this particular structure, there are 34 million entries. In this case, that M is million, not meg. And 48,000 of them are currently in use. And then we look at the group buffer pool, and again, we can track requests and whatnot. But the big thing about the group buffer pool here is the last column is directory reclaims and cross invalidations due to directory reclaims. And I like the fact that these are 0. This column here applies to any of these structures, right? The average request per second. And we'll see in this particular scenario, the lock structure has more requests per second than the group buffer pool. And in most customers, I see the difference being significantly larger than this, right? So 10, 50, 100, 200,000 requests per second for the lock structure, and the group buffer pools, in the thousands or tens of thousands. This page is just the notes, right? This is what those arrows mean on the previous page. So if you're watching this later, or if you're looking at the presentation that I uploaded, this will tell you what those arrows are supposed to mean. The processor summary, I just have this one example. In this particular case, this processor was 2.6% busy over the interval, and it had 3 engines. So I love seeing this, right? This is a really nice number, lots of capacity on this CF. I have seen them where they are 60% busy, and that's generally a bad idea. When CFs get 60% busy, you're going to start seeing a lot of delays, and synchronous service times will elongate. The next section that I care about as we go into port is structure activity. Structure activity includes information from each LPAR as well as a total for the structure. Now, I have overwritten the actual system name so as not to give away any interesting information about this customer, but they have a 5-way data sharing environment. And the first thing I want to bring your attention to is on the lower left, the total number of requests for the interval, and then the 5206 is the requests per second. This matches what we saw in the structure summary. Then for each LPAR, we're going to see the synchronous service time for the requests. And you can see once we get into ZOS 3 or ZOS 4, the percent of requests, so the number of synchronous requests are not the total number of requests. There are some asynchronous requests as well. And the sync service time has climbed appreciably. So in ZOS 1 and 2, the sync service time was a little over 2 microseconds. And in 3, 4, and 5, it's well over 20 microseconds. And the reason for that, as we'll say on the same page, is in this environment, the CF that, the engine where ZOS 3, 4, and 5 resided was some distance away, right? About 2 kilometers away. So that quickly adds 20 microseconds of round trip. The other thing to note here on the right is external request contentions. And this is where we see what the false contention is. So we compare the false contention to the total requests, and we would like it to be less than 1% if possible. And if it isn't, then if you make your lock structure larger and make the lock table larger, that will reduce your false contention, because basically there'll be more entries to spread the requests around. Again, these are the notes to go with those pictures so you can take a look at these after the fact. Group buffer pools, similar concept, right? Each of the 5 systems is putting in entries. We have our total requests and requests per second, and we can see that the sync service time, and then group buffer pools often have some asynchronous components, not as many, but probably more than the lock structure does. And again, we can see that the sync service time for ZOS 3, 4, and 5 is higher because these systems are at another site. When I look at the data access, this is a portion of the structure activity that the lock structure does not have. This tells us overall, how many reads were done to the group buffer pool, how many writes, and how many castouts. If the only non-zero value here is writes, then you're looking at the secondary group buffer pool. All right, group buffer pools should be duplexed, and the secondary group buffer pool is only tracking changed pages. So all you will see in this section is writes. And these are the notes to go with that page. I'm going to talk briefly about CFRM policy entries. So I've got an example CFRM policy entry for the lock structure. And in this case, size, or 2 gigabytes, is the largest possible allocation for the structure with this CFRM policy in effect or active. Init size is the initial allocation that XCS will use. And then with this kind of definition, you can use setXCF commands, right? Those are commands through XCF to do things with the CF and the structures. And so you can increase the allocation anywhere from 1 gig all the way up to 2 gig. If you do that increase manually, the only thing that will be increased are the record list entries, where the RLM and XCF and the lock structure track detailed information about things that are being changed. And these are protecting data in case you lose the DB2 or the RLM, right? These become retained locks, so that an update that I was in the middle of making doesn't get lost just because my DB2 failed. If you need to increase the size of the lock table to reduce false contention, you need to at least double the structure size and then rebuild the structure. The allow AutoWalt says XCS is allowed to make its own adjustments between init size and size. And theoretically, it could adjust down to min size if you have contention for storage on your coupling facility. Now, when XCS increases the size, it only will affect the record list entries. And XCS adjustments are not intended for spikes. I have a long war story that I won't get into, but a customer went from 80% full to 100% full in 12 seconds. And XCS will not respond that quickly. In DB213, the IRLM can trigger an allocation increase. And those IRLM will track how full the structure is getting, and will request the increase in size more responsibly than XCS would. Finally, the full threshold, which isn't mentioned here, is because this customer didn't have it. If you set full threshold greater than 0, then XCS will monitor the structure size, and at whatever value you put there, that's when XCS thinks that the structure is full and should consider increasing the value. So this example doesn't have duplex. So where is it? Well, it didn't get listed, so it's picking up the default duplex disabled. And duplex disabled is a typo. There should be a D at the end of that. A duplex disabled is appropriate for the lock structure and the SCA as long as they're allocated on an external coupling facility, or at least on a coupling facility that's not on the same system with your DB2 members. If you have a 2CAC, 2 system, 2 piece of hardware configuration, and you have integrated coupling facilities on both of them, duplex enabled is the recommended approach. This is called system managed duplexing because it's XCS that's managing 2 copies of the lock structure and 2 copies of the SCA. So you have availability even if one of your systems fails. You avoid a single point of failure. Now, the thing about this is that for the lock structure, duplex enabled is very expensive. We call this synchronous system managed duplexing, and it drives up the cost. The synchronous service times go up, depending on the environment, something like 3 times or 4 times, which becomes noticeable to your host CPs. So if you're in this kind of configuration, you should look at asynchronous system managed duplexing. Martin had some charts about this in his presentation earlier today with some interesting numbers. So I suggest the customers I work with who are interested in this, that they set up duplex enabled async only. And that says if they can do async, they do async. And that way they get the response times much closer to where they are in simplex mode. And there are a number of customers who have experience with this. There are more. I'm working with several customers even as we speak on getting this implemented. Let me bring my mouse back to where it belongs. Here's an example for the group buffer pools. Now, for this customer, they included allow AutoVault yes, and they included duplex enabled because we strongly recommend duplexing group buffer pools. This is an availability thing, right? If you lose a group buffer pool, you lose all those changed pages that haven't made it out to disk yet, and that can lead to a lengthy recovery period. So we strongly recommend duplexing group buffer pools. Group buffer pool duplexing is user managed duplexing. And in this case, user means DB2. DB2 is a user of XES services. There's minimal performance impact of duplexing your group buffer pools, so please do it. Again, allow AutoVault says XES can make the structure larger, or in the case of group buffer pools, it can adjust the ratio of directory entries to data elements to make sure you have an appropriate number of each. And if you have stress on both, XES can increase all the way up to your size specification. If you don't say allow AutoVault yes, then you have to issue setXEF commands to increase the size of the structure, and you have to manually adjust the group buffer pool ratio for directory entries to data elements. And doing that manual change, right? You can do that, alter group buffer pool to set the ratio to a different value, but then you have to rebuild the structure. And during structure rebuild, you're probably going to see, elapsed time increases for the applications that are using that buffer pool. So allow AutoVault yes has been out, I want to say, since the late 90s, 2000, and I strongly encourage you to use that both for lock and SA and for the group buffer pools. All right. Now let's look at some DB2 displays and reports. Depending on who's in the audience, you may or may not be familiar with these already. My favorite display is the display group buffer pool. And there are 2 levels that we can do this display. One is the group level. The first example I have here says type gcon. In other words, only tell me about the group buffer pools that are actually connected, not the defined ones that I'm not working with right now. And gdetail says, give me details for the group. And the asterisk says, since the group buffer pool was allocated. So that could be days or weeks or months ago. And that gives me a high level view. Okay, what all's happening here? I get a lot of definition information, plus I get some statistics over a period of time. The second example just uses the word interval. And you don't even have to specify interval if you just leave this off, it defaults to interval. And if you issue that message twice, let's say an hour apart, then the second message will just have the statistics for that hour. So I find this very useful if I'm looking for some information about peaks. I might look at an hour peak during batch, an hour peak during the onlines, and that gives me some information to help me decide what I want to focus on when I look at more detailed information minute by minute available in the SMF records. If I haven't defined my group buffer pool correctly, I may get some problems, right? I may get some directory entry reclaims, which we talked about back in the CF report section. And those aren't nice. That means there aren't enough directory entries and we have to steal them. And that leads to more messaging. It's not horrible, but it's not good. But if you do enough directory entry reclaims, it may be that you are cross-invalidating someone else's page that was being tracked by that directory entry. So if I cross-invalidate pages, that means a page sitting in someone's local buffer pool that's a perfectly clean page gets marked invalid and they can't use it. And if they do need the page again, they're going to look for in the group buffer pool and it won't be there, which means I'll have to do IO. So cross-invalidates due to directory reclaims can lead to increased synchronous IO. And of course, everybody knows that's not a good thing for application performance. And then the third thing that might happen if we don't define a group buffer pool well is that we get writes fail due to lack of storage. And what this means is we're trying to write a changed page at or before commit out to the group buffer pool, and there's no room, right? It's full of change pages. We haven't been casting out enough, so we can't steal any. And DB2 will retry numerous times to get that page written. And if it can't, it gets added to the logical page list, and then no member can access it. So if it's just retries, that's an application delay. If DB2 gives up and puts the page on the logical page list, that's much worse than a performance problem. That's now an availability problem because no one can access that page until you go through LPL, logical page list recovery. So what does this look like if we do this display? Well, here's an example of the display. And the display, of course, takes up multiple screens. So I've just got part of the initial part of the display, which is mostly status information. And this will change very infrequently. And just for example, I'm highlighting here, in this particular case, they have a directory to data ratio of 26:1, which suggests to me that AutoAlt is enabled and XES has been doing this on their behalf. So there's very good information here about the structure allocation. But to see whether or not it's doing well, we need to go to the right section. And the 3 highlighted fields should be 0. These are the ones we talked about on the other page. So writes fail due to lack of storage should be 0. This example it is. Reclaims for directories should be 0. And here it is. And then cross-invalidation due to directory reclaims, also 0. So this is how it should look. And if you don't have zeros here, then you need to do something about it. What is the easiest thing to do about it? Well, make the group buffer pool bigger. That's the easiest thing. But you may have to evaluate whether you want to change the ratio, or change how if you get a write failure, maybe you need to change how often the local DB2s are writing so that spikes and writes to the group buffer pool are smoothed out. There's a number of possible ways to address that. The display group buffer pool also has information at the member level. You see, we changed this word from gdetail to mdetail to get the member, and then interval, which is the default, you don't have to say it. If we do this command twice, the second one will have information about the interval. And there's a lot of information in here at the member level. It's quite interesting. And what I care about the most is the hit ratio for reads when the local buffer pool page is cross-invalidated, and the hit ratio for reads when the page was not found in the local buffer pool. There are other interesting fields too. So let's see what these things look like. So first of all, let's look at reads due to buffer invalidation, data returned and data not returned. This is the case where I have a page in my local buffer pool that got marked invalid, right? Martin changed the page, so now my page is invalid. And I go after the group buffer pool to find it. And how many times is it there? That's A. And how many times is it not there? And that's B. So if you take A and divide it by A plus B, that gives you a ratio of your XI, your XI read hit ratio. And that is an appropriate tuning target. We like that number to be high. If I don't see that at least in approaching 90s, if not in the mid to upper 90%, my customers, I encourage them to increase, well, generally to increase the size of the structure, but there might also be other adjustments. The other read hit ratio is the not found ratio. So this is, I looked for a page, it's not in my local buffer pool, but because that page set is group buffer pool dependent, I have to look in the group buffer pool to see if it's there. And so the item labeled C says data was returned. So I found something there. And the item labeled D said the data wasn't found. And you can see it wasn't found, 1.7 million times, and only found it 148,000 times. So in this particular customer scenario, C over C plus D is just under 25%. So I would not consider that a tuning target, right? That's a lucky benefit. I see a lot of numbers very low here. However, if you have lots of CF resource, you may consider increasing the size of the group buffer pool in hopes of nudging this up, right? But if it doesn't nudge, if it doesn't increase with as you increase the group buffer pool size, then probably your workload pattern isn't going to respond well, and so there's no sense increasing it just for that. So increasing it for the A over A plus B makes sense. The other one, maybe you get lucky. Now, so that's one way to look at it, is to look at all these displays. But what I like to do when I look at customer data is I take their SMF 100 records and extract them out and turn them into graphs. In my case, I take advantage of a Megamon to do this and produce some CSVs, and then I graph this out. So in this particular graph, I've got the blue, or whatever that color it is, the blue line, which is running against the left axis, and that's the percent of my read hit ratio for XI, right? So my cross-invalidated pages, when I went to look for them, were they in the group buffer pool? And so I would like that to be as close to the 100% line as possible. And then the orange line is how many of these XI requests am I making per second, right? If I have a buffer pool where the number of XI requests is very low, then I don't care about the ratio. But if I'm doing this a lot, then I care. So this particular scenario, we're spiking up to about 350 requests per second on that one spike right about here. Oops, right about here. And then during the online hours, we're getting 200, 250 per second, and we're getting pretty good read hit ratios there, right? So we're getting a good ratio during the online hours. During the batch hours, it's a little inconsistent. The ratio gets quite sporadic. And in general, the requests are lower, but there are some spikes during the early morning batch. And so this is something where, if you're having batch performance challenges, or you're trying to get the batch processes to complete sooner, you might try and nudge these numbers up by increasing the size of the structure. On the other hand, it's possible that your batch workload isn't reusing the pages, right? So as they get marked invalid, they're not getting touched again, or they're not there long enough, right? So there's a number of different things you can think about, and this is one way to go after this data. If you want to improve the read hit ratios, the easiest thing to do is increase, or the target would be to increase the time that the pages, right, the 4K, 8K, 16K, or 32K pages are residing in the group buffer pool. And the simple way to do that with version 12 is you make the group buffer pool larger and measure it and see if it worked. In DB213 and coupling facility code 25, which is on the Z16 or beyond, we'll report on page residency times, right? Group buffer pool residency times for data elements and for directory entries. So let's talk about that briefly. That residency time is going to be tracked in IFCID 230, which is part of DB2 Statistics Class 5, which almost everyone has on. And if you don't, in your data sharing, you should. You can also see this in a display group buffer pool G detail, because it'll track that information. The higher the number, the better, because that means that the element, whether it's a DB2 page or the directory entry, has been sitting in the group buffer pool a long time. And the longer it's there, the greater likelihood that it'll be there when another process needs it. There is an exception to this higher the better. 0 means that the page, that the resource, the data element or directory entry has never been stolen, right? That's better than 100 or 1,000. 0 is the best. But any non-zero number that's a small number, then that means your resources aren't sticking around very long. So in DB213 and CFs that are allocated on Z16 coupling facilities, you can track this for your group buffer pool resources by group buffer pool. Okay, we are getting near the end. I've got a few suggestions. First of all, for your coupling facilities and structures, and if you're a DB2 person, some of these things may be out of your control, but you can certainly communicate with your ZOS team or your capacity and performance team. The first thing is I like to see dedicated processors for production CFL PARs. In a non-production environment, maybe I've got a test data sharing group or a QA data sharing group or a development data sharing group. It's possible that I would be willing to share the processors between CFs because they aren't as busy, but in production, I want the processors dedicated, and I want at least 2. And in some shops, they need 5 or 6. You can't realistically go above 8 until you get to Z16s, and on the Z16, the curve, as you add CF engines, doesn't flatten out at 8. It keeps increasing. For sizing your structure, you should start with the CF Sizer tool. It's irritating because it doesn't remember what you did the last time you used it, unless you use ZOSMF to size your structures. I should have added this entry here. With ZOSMF, it will remember what you did last time so that you don't have to figure out new values, and you can just make some adjustments to get what you want out of it. But start with the CF Sizer tool for your SCA and your lock structure and your group buffer pools. And what I do is I take the output from that tool and I round it up to a friendly number, and I make that my init size. And then I define the size larger than that, somewhere up to 2 times the size. In the case of the lock structure, I would for sure make it 2 times the size. For group buffer pools, anywhere between 20% and 100% of init size. Use duplex enabled and allow auto alt yes for group buffer pools for sure. Use allow auto alt yes for lock and SCA. And then the duplex setting for the lock and the SCA depends upon your coupling facility and or your integrated coupling facility configuration. So this is an availability issue as well as performance issue. So Martin talked earlier today about async coupling facility duplexing. And the thing I think I've got some more about the duplex setting for the lock and the SCA in the next slide, I hope. No, I don't. The point about duplexing is this. Going back to earlier when we talked about a 2 KEK, 2 ICF configuration, you need to duplex the lock and the SCA in that situation. And you can asynchronously duplex the lock structure, which is going to perform much better. This whole async CF duplexing is another hour presentation, which I'm not doing right now. Finally, monitor your DB2 structures, right? Monitor for synchronous service times, async conversions, and include false contentions when looking at lock 1. So looking at synchronous service times and async conversions and what the value should be will depend on your configuration, right? I've looked at shops where their systems are very close to each other, and sometimes they have the lock structure on the same footprint, and even with async CF duplexing, that can be quite a small number. And if it isn't on the same footprint, if it's an external CF and it's very close, they can get in the order of 3 microseconds lock service time. For contention, you would like real contention to be less than 2% of requests and false contention less than 1% of requests. There's not much you can do about real contention except for work with your application teams. But with false contention, if it gets high, you can increase the size of the lock table. And the easiest way to do that is to double the lock structure allocation and rebuild the structure, because by default, it'll increase the size of the lock table. For group buffer pools, you want to monitor synchronous service times and async conversion. If you're getting too much async conversion, you may have some issues. It might be a distance issue. It might be a CF busy issue. I remember early on that same 2008 customer that had 166,000 lock requests per second. They had an over busy CF, and it was so busy that they were getting 10 microseconds more service time on all their group buffer pool requests. And no, I can't hit a stopwatch that fast. But when you have heavy production work going through, and each request to the group buffer pool takes an additional 10 microseconds, that's very noticeable. Within the group buffer pools, you want to monitor at the group level for write fail due to lack of storage, directory reclaims, and cross validations due to directory reclaims. And at the member level, monitor your XI read hit ratio and your not found read hit ratio. And most importantly, ensure that your DB2 team and your ZOS team or your capacity performance planning team, whoever owns the coupling facilities and the various resources associated with the coupling facilities, make sure these teams are communicating. Because sometimes it's not obvious to the one that something critical is happening that's going to affect DB2 performance. For example, it may or may not be the case that the ZOS team is monitoring the usage summary portion of the coupling facility activity report for the group buffer pools and doesn't notice the non-zero value for directory reclaims and crossing validations to directory reclaims. And it's possible that the DB2 team isn't checking the group buffer pool output for those values unless ZOS notices and says, hey, you've got a non-zero value here. And then the DB2 team can go investigate and start tracking. So make sure you communicate early. So I've been speaking rapidly, which means we have time left for questions. So Martin, I didn't hear any interruption along the way. So either that means no one entered a question in the chat or you were able to type the answer without interrupting me. So
Or I was in a coma. It's after lunch. No, that wasn't
the post-lunch coma, exactly.
I was paying attention, and by the way, you've got a nice large audience here, so part of it was that. So, has anybody got any questions for Mark at this stage? While people are thinking about that, Mark, do you want to paste your email in, and I'll paste the evaluation in as well?
So I can type it in. I have to stop. What do I have to do? I have to exit this so I can type it into the chat. I will type it into the chat here.
Meanwhile, I'll go and find the feedback link.
For whatever reason, I had to respond to a message. So there's my email. In case it wasn't obvious, I love talking about data sharing and parallel sysplex and all these things. So if you do have questions, let me know. I'm especially interested in helping folks think about asynchronous log structure duplexing, because I think there are a number of customers who should be doing system managed duplexing and aren't. And async duplexing is less painful than synchronous system managed duplexing. Andre has a question about the CF activity report. Is it part of RMF? Yes, so I didn't label it the RMF coupling facility activity report, but RMF produces it. Other vendors also will produce a report that's extremely similar with almost all the fields. They tend to put the order of the different report sections slightly different, but the same data is available.
Right, and it's all based on SMF 74 subtype 4 that both
right.
RMF and CMF will cut. Slightly different in two cases, actually, but very
so if you have programs like Martin, you can go right after the 74 subtype 4 records.
This is interesting. He wants me to confirm my speaking language and thinks I was speaking Arabic. Okay.
All right.
Right, here we go. Another question.
Okay, another question here. What's the directory size at the latest CF level? Now that's a fine question. That is a question. I haven't kept up with how large a directory entry is in a long time. And here's why. I know how large the data elements are, right? They're 4K, 8K, 16K, or 32K. And in a display group buffer pool or other places, I can find out how many data elements I have and how many directory entries I have. And I know how large the structure is. So you'd think that if I take the structure size and subtract the page size, I would get the remainder and divide by the directory entries to get their size, but that's not true, right? There are control elements. I think of them as at the bottom of the structure. I'm not sure where they are, but there are control elements that XCS uses to manage the structure. So they take up some space. So if I subtract out the data elements, the pages with the change data, I can't easily do a division and get the number. And the number changes with each CF level. So it's an excellent question, and I don't know the answer for CFCC 25.
Do you have a view from a previous CF level that we could say, well, it's going to be a bit more than that, probably? Because at this point, I'm not sensitized at all to the size of it.
Right. Way back when, and I want to say mid-90s, I think it was about 256 bytes. And I'm sure it's larger than that now. I just don't know how much bigger. It's not a number I use to calculate group buffer pool sizes. If
Right.
I'm working with a customer to size their group buffer pools, I'm going to be looking at it a different way, right? I'm going to be looking at it from the point of view of how many pages I want in there and how many directory entries do I need for those pages. And then I put that into CF Sizer, and it tells me how big to make it. And then I make the structure a little bit bigger for init size.
Yeah, the max sizes that you mentioned is interesting because I just want to relay a conversation I had with Mark Brooks a while back, which is you don't want to make the max size more than, as you say, about twice the current size, because it's filled with control blocks ready to go, and you end up with not much space for data if you oversize the max size.
Right.
Right. That's where I think 2x comes from.
Yes, exactly. We discovered this in, I would say, the mid-90s, when everything was small and nobody knew how big to make these things. And so someone said, oh, I'm going to make my group buffer pool this size, which is, I think, what it is, but I'm going to allow myself to grow up to 10 times. Well, immediately it wasn't big enough because most of it was filled up with the control structures to allow it to go to 10. And yes, there was nothing left to do any work with. So it was immediately too full and they had to make it bigger. But yes, that's why we say up to 2, right?
Yes.
And if you need more than that, you just define it bigger. All right, let me see if there's another question here. I don't see another one coming in yet. And I think we have 1 minute left. So there's 1 minute left for additional questions. Or if you think of the questions later, send me an email. Love to answer them. And if you have really important things and you are willing to pay for me to come across the pond, I'll show up and present to you, especially on async CF duplexing.
Especially if there's a pub in the area where it'll be frequent.
Pubs are appreciated.
The brave old oak or the boo is the fave. Yeah. Okay.
Yes.
Any more questions?
Thank you. Thank you very, very much, everyone, for your time. Enjoy the rest of the conference. And if I'm really lucky, I'll see some of you in person.
And we have Keziah presenting in half an hour's time. So back at 3 o'clock for Keziah to present on DB2 and WLM.
All right. Thanks, Martin. Thanks, everyone.
Bye-bye.
Bye.